Hi everybody, we're now going to talk about using this regression line for the purposes of description and prediction. So our basic line gives us the expected temperature given an intercept plus a slope times the number of cricket chirps per minute. In the language of algebra, we use y hat equals b naught plus b1 times x. So x are raw values of our input or predictor variable. Y hat, those are the predicted or fitted values of our outcome variable. B naught or b subscript 0, that is our intercept. And then b1, that is our slope. It's our rise over the run. And the thing to keep in mind is what we're predicting here. It's the expected mean of the outcome, conditional on the different values of x. So in this case, the intercept is 37 degrees Fahrenheit, and the slope is 0.23, which reflects the rise over the run. You can think of this little model. It's a basic model of reality. It's an abstraction, but it helps us to understand and approximate a process that we observe in the world around us. In this case, it's this relationship between cricket chirps per minute and the temperature. And this line we can use for the purposes of prediction in new contexts. So you create a line based on some set of data, and then you can use this regression model, this fitted line based on the intercept and slope, in new contexts. So you can go out in a new environment and just say, oh, the number of cricket chirps per minute is 100. And I can use this model that we created based on previous observations to predict, to make a guess about what the current temperature really is. So what are we modeling? We're modeling the conditional mean. This is probably the most misunderstood part of simple linear regression. All you're doing is you're modeling the mean of the outcome conditional on different values of x. Specifically, y hat, that gives us the expected mean of the outcome, given whatever value of x you put in. This is very useful for describing our sample or population of data. So let's talk about using this regression line for the purposes of description. So you might say, what is the expected mean or estimated mean temperature in Fahrenheit if the number of cricket chirps is 100? This is a conditional mean. It's if x equals 100, what is y hat? What is our expected mean? Well, we can use the regression line. All you do is you just put in, you plug in a value of x equal to 100, and you multiply 100 times the slope plus the intercept. And with that calculation, we find that when x equals 100, you can go up to the line, and then you look over at the value of y. That is 60.68 degrees Fahrenheit. So we can say that if the number of cricket chirps outside is 100, then the expected mean temperature is about 60.68 degrees Fahrenheit, which is pretty useful because this is a way of using cricket chirps per minute as a thermometer. You might say, what is the expected mean temperature if the number of cricket chirps is 0? If we just set x equal to 0, we get about 37.68 degrees Fahrenheit. This is the intercept, right? The intercept is when x equals 0. Crucially, it's the mean of the outcome. It's the expected mean of the outcome when x equals 0. So when there's 0 degrees Fahrenheit, when there's 0 cricket chirps per minute, we expect the degrees Fahrenheit to be about 37.68 degrees Fahrenheit. And you can see this. You can just look on the actual plot, find x equal to 0, move up to the line, and follow over, and that's about 37.68 degrees Fahrenheit. You might also ask, what is the difference between certain mean temperatures given different values of x? So we might say, what is the expected difference in the mean or average temperature if the number of cricket chirps is 100 versus 101? So we can just put in these two different values into the equation and calculate the difference. So when x equals 100, when the number of cricket chirps per minute is 100, then we get 60.68 degrees Fahrenheit. When the number of cricket chirps per minute is 101, then we get 60.91 degrees Fahrenheit as the expected mean. The difference between these two values, if you take 60.91 and subtract out 60.68, you get 0.23. That is the slope. So the slope is really giving us the expected difference in the mean temperatures for a 1 unit difference in our x variable, right? And you can see this in this graph. Okay, we have these two different points on the line, right? And that all that slope is giving us is it's giving us that expected difference. So in means, the intercept gives us the expected mean of the outcome when x is 0. When the number of cricket chirps is 0, that's the intercept. The slope is the difference in expected means of the outcome for a 1 unit increase in x. Typically people say, they just interpret the slope as saying for every 1 unit increase in the x variable, right, the outcome is going to increase by whatever the value of b1 is, whatever the value of the slope is. So in this case, we would say for every 1 unit increase in cricket chirps per minute, the temperature we expect to increase by 0.23 degrees Fahrenheit. Crucially, notice the sign of the slope. Positive slope indicates an upward line. It suggests a positive linear relationship. A negative sign on that slope suggests a downward line, a negative linear relationship, while a slope of 0 suggests a horizontal line. Notice that if the slope is 0, in fact, x times that value is 0. So in that case, the regression model is really, it just has an intercept. Right? Interpreting the output, let's just look at this output again, because it's very useful to understand how to interpret regression model output. Here we have the output from statistical software. And from this output, we've given these two values of what we call the coefficients, the intercept and the slope. The slope here is chirps. Okay. The statistical software tells us the name of the variable when it refers to the slope in this case. And then the intercept is 37.8 roughly. What the intercept tells us, it tells us the expected mean temperature when x equals 0. So in this case, we expect the mean temperature to be about 37 degrees roughly when there are no cricket chirps. The slope tells us for every 1 unit increase in temperature, right, for every 1 unit increase in cricket chirps, the expected mean temperature is going to increase by 0.23 degrees Fahrenheit. So for every 1 unit increase in cricket chirps, the expected mean temperature will increase by 0.23 degrees Fahrenheit. Now we can use regression and interpret it in terms of describing. We can also use it for prediction. It's a subtle difference, but the idea with prediction is that you use a set of data to create this regression model. Then you go out into the field again, and you just count the number of cricket chirps per minute, and then you just use this line. Okay, you don't actually measure the temperature. You just use this line, this model, to make a guess about what the temperature is. So, and that's because this regression line, you can think of, it's a predictive model, right? So if you were to go outside and you were to, you counted the number of cricket chirps per minute to be 110, what would you predict the temperature to be? Right? Well, we can just use this model, right? In this case, the number of cricket chirps per minute, if it's 110, then the temperature outside is about 63 degrees Fahrenheit, okay? This is seen in this graph. You can see that we're really just using the regression model the same way as before, but the idea is that you're using it in a new context when we talk about prediction. You might say, well, what if we were to go outside and counted the number of cricket chirps per minute to be 130? Well, what would the expected temperature to be? We'd expect the temperature to be about 67.58 degrees Fahrenheit. Then you might say, what would we predict the temperature to be if the number of cricket chirps were 103? Well, if the number of cricket chirps were 103, we would get roughly 61 degrees Fahrenheit. You just plug in that value of 103. But you can see in this case, we actually have a data point for 103. Meaning in our data set, we actually have a value of x that's 103. And you can see that our predicted value of y hat is about 61 degrees Fahrenheit, but our raw value of y is in fact 63.5 degrees Fahrenheit. You can see that our prediction is off. Right? The y hat is different from our raw value of y. To put it another way, our raw observed actual values of the outcome of temperature are in fact different from our fitted or predicted values of temperature. And this should be clear because those y-hats, those all lie on the line. And you can see that the actual data points, they're a little bit above, a little bit below. They're not always directly on the line. So we're a little bit off. Is there a way we can talk about being slightly off in terms of prediction? Well, there is. The difference between the raw values of y and our fitted or predicted value, our y-hats, those are called residuals or errors. We label these little e. So in this case, you can see that the raw value of y, when we go to the data set and you look at when x equals 103, you can see that the raw value is going to be, in fact, 63.5 degrees Fahrenheit. But based on this regression line, the fitted value is about 61 degrees Fahrenheit. That difference between our raw value and our predictive value, that's about 2.5 degrees Fahrenheit. We call that a residual or error. It's a residual because you can kind of think of it, it's what's left over after we use our line for prediction. To put it another way, it's an error. Okay? It's how off we are. If we use this model for prediction, we're going to be off. In this case, we're off by about 2.5 degrees Fahrenheit. Not terribly far off if you're, if you're kind of like using, if you're a farmer and you're going out in the field and you're using this to predict temperature, it's not too bad. 2.5 degrees Fahrenheit, it's not too far off, but we are off. There is an error. There is a residual. And you can really, as we'll see in just a bit, you can use these residuals, these errors, to understand how good of a job your line is doing in terms of fitting to a scatter plot of data. So here we have this idea of fitted versus residual values. You can think of our outcome as being split into these two components. So for a sample of data, we have our raw value of our outcome. This is the full value of the temperature. And you have that part of the outcome that's based on the fitted or predicted value, and then you have what's left over, the residual error. So you can think of your outcome being divided into these two components. If you have a population, you use a slightly different notation, but it's the same concept. You have the y-hat, you have that fitted or predicted part of the outcome, and then you have this error. You have this residual. And the idea behind it is that the residual or error, it just tells us how far off each observation's outcome value is from the line for a given value of x. So when x equals 103, we're going to be off by about 2.5 degrees Fahrenheit. That is the error term. That is this value of e for that particular value. Another important point is that we like to sometimes keep that little I there to remind us that each observational unit, each row, has its own value of x, y, but it also has its own value of y hat and its own residual. Each observation in this data set, each of those 7 observations, they have a different predicted value of y and they have a different residual. So our regression model, if you recall, is the y hat equals 37 degrees Fahrenheit plus 0.23 times x. That's simply the intercept plus the slope times our raw value of x. Now you can notice for each row of this data set, we have a different y hat, we have a different predicted value. All that's telling us is that each point has its own point on that line. It's its own location on that line. So when x equals 1, when we have I equal 1 for x, then we have this value of 56.36 degrees Fahrenheit. The y hat for that first person is 56.36 degrees Fahrenheit. For the second row, for that observational unit, you just plug in the value of x, which is 97, and you get this value of 60. And then you can see that each row has its own value of y hat. We're simply plugging in the value of x and churning out this predicted or fitted value of y hat. These are the expected means for each of these different values of x, because the regression model, keep in mind, it's giving us the mean of the outcome conditional on the value of x. And so we're just conditioning on these different values of x. We're saying, well, what is the expected mean when x equals, for example, 150? That's the 5th row of this data set. Well, in that case, the expected mean temperature is about 72 degrees Fahrenheit. So for now, the important point is each observation has its own y hat. Each observational unit has its own x value, y value, and its own y hat. In a similar way, each observational unit has its own error or residual. Each data point is off by a little amount. So our residuals are simply the raw values of our outcome, and we subtract out the y hat, the fitted or predicted value. So for I equals 1, for that first row, we have a residual of negative 1.86. And we can see that some residuals are negative, some are positive, and they really differ. The key point here is that I would say the residuals are all pretty close to the line. Right? Keep in mind that we're predicting a temperature range of, let's say, 30 to 120 degrees Fahrenheit, and yet the residuals are all pretty close. Each of these residuals are telling us how far off we are in terms of the regression model. So when we have a negative residual, right, it's simply telling us, in this case, that our y hat is a little bit larger than our value of y. When we have a positive residual, it's telling us that our raw value of our outcome is larger than our y hat. So you can see that we have values of y hats that are either above or below. Or to put another way, we have values of y that are either above or below our y hats. So here's our model when we talk about this concept of residuals as well. We have this basic regression model in which we have an outcome that we can partition into these two kinds of sources. We have the fitted or predicted value of our outcome, and then we have the residual. The fitted or predicted values lie on the regression line, and then the errors, that's whatever is left over. Right? It's the raw value of our outcome minus the actual fitted value. Then we can also talk about the fitted part of the outcome described in terms of this regression line, which consists of an intercept plus a slope times the raw value of x. And so in this case, the intercept is 37 degrees Fahrenheit. So when x equals 0, the expected mean temperature is 37 degrees Fahrenheit. Then we have this rise over the run. So for every 1 unit increase in the number of cricket chirps per minute, the expected outcome, the expected mean temperature, will increase by 0.23 degrees Fahrenheit. And then we have this leftover stuff, the residuals. All those data points, they're all pretty close around that line. But in some cases, the y hat is below. In some cases, the y hat is above its relative value of y. Okay? So for this residual that we've labeled, the y is below the y hat. In other cases, the y is going to be above. And these residuals or error terms, they give us an idea of how far off on average we are from our raw values versus the fitted or predicted values of y hat. So let's think about Dolbear's law again in the context of this simple linear regression line. We've concluded, using this sample of data, that we can use cricket chirps to describe the data set, but we can also use it to predict the temperature in potentially new contexts. In general, the more cricket chirps per minute, the higher the expected average temperature. We know this because that slope is positive. It's 0.23. So for every 1 unit increase in cricket chirps per minute, the expected temperature is going to increase by 0.23 degrees Fahrenheit. And it's a positive linear relationship. And you can see that the line does a pretty good job on this set of data. Our predicted values, our y hats, differ from our raw values of y by only a few degrees. Right? Sometimes the y is above, sometimes it's below, but they're all pretty tightly bound around that line. So for this first part of today's lecture, there are a few key points. Simple linear regression, sometimes classical linear regression or bivariate regression, it's simply a technique for fitting a line to a scatter plot of data. When we run a simple linear regression model, we're modeling the mean of the outcome conditional on different values of an input or predictor variable x. The difference between the fitted values and the actual values of the outcome, those are called the residuals or the errors. These errors or these residuals, they give you an idea of how far off you are in terms of predicting or describing your set of data. And in that context, regression is very commonly used for the purposes of description. So you're trying to describe the mean of the outcome conditional on different values of x in a set of data. But you can also use it for prediction. Once you create a regression line, you can use it in new contexts. Just to say, well, I don't know what the temperature is, but I know the number of cricket chirps per minute is, say, 100. And then you can use this model to predict. So with that, we've really finished our discussion of introducing the idea of simple linear regression. In the next segment of this lecture, we will talk about how we came up with these different values of the intercept and slope, because there are many different lines you can fit to any single scatter plot of data.